This is where our curriculum really comes alive, when you take what you learn in the classroom and apply it to solve real-world problems.
So we utilize the principles of these large language models in implementing our web application. So it's the basis of what we use to create a chat completion.
In our research, we have discovered a problem with how virtual machines schedule tasks on their virtual CPUs. In the fall, we'll be making a bot to interact with people through chats. And in the spring, hopefully we can test a model with one or more intuitive step time.
And the model I trained achieved a result of 81.22% with minimal training. There's much more training to be done in that regard.
The Star cluster at Hofstra, we have 2 Apollo 6500 nodes from NVIDIA, and which the nodes themselves have 64 cores and 1 terabyte of RAM.
Based on it, we designed 2 instant proof of reserve protocols. One is non-intrusive, which works for cryptocurrencies such as Bitcoin, where transaction details are public.
So specifically, I've been using convolutional neural networks, which are an application of deep learning in computer vision to parse imagery.
Using our research and the code that we've developed and the image processing methods that we have, we're able to determine the development of fetuses' lungs at different ages through ultrasound images.
So picture A is showing basically the graph without any flow to it. It's just static for 24 to 48 hours. And then picture B is showing after flow, and you can tell there is some sort of decrease in cells, but there's still endothelialization occurring.
So the aim of this research project was to assess the novel plant-based three-dimensional vascular grafts that Dr. Myrna's lab group are creating, and to use ultrasound imaging to determine several factors about these grafts.
So my project's research goal is to use the hair biologics that get wasted for biomedical applications, specifically in mesenchymal stem cell culture and differentiation.
I created an accurate and reliable real-time pressure monitoring system, and I could monitor it both in person and remotely. I was able to detect leaks, air bubbles, and non-vascularizing vessels, which, looking back, can save me a lot of time, as I can stop experiments if I see any of these things going on.
The main goal of the project is to create a tissue-engineered vascular construct which has durable and stable vessels, but we also want to see how flow affects the vessels themselves as well.
So we started by drawing this out in CorelDRAW. We laser cut the front panel design, inserted the circuit components into the breadboard, which you can see, and connected potentiometers and inputs to the front panel.
The goal was to have multiple power amplifiers going across, so that we can try to enable us to steer the radiation pattern.
So this is the quadcopter that we built from scratch. We mounted it on a ball joint to get a better sense of how the various degrees of freedom relate to the different actuators.
Some of the conclusions that we came at the end of making our prototype is that having a laser measuring tool equipped with a camera was the most effective in completing our objective.
So some of our conclusions, a rotating baseball never achieves a change in direction of the side force regardless of the spin parameter, Reynolds number, or turbulence level. The seams prevent asymmetric boundary layer separation and reattachment required to reduce the Hilder's Magnus effect.
Using all of these variables, we're able to determine the permeability coefficient of the soil, basically how it's a measure of how fast the water will go up through the soil. And we're able to determine the ultimate bearing capacity of the soil at various water levels.
I really want to congratulate the students and the faculty mentors for the tremendous time and effort they put into these projects during the summer. And I hope students who participated realize that when you put energy, time, effort, and passion into something, it's incredible what you can accomplish.